The goal of this example is to determine the design wind loads associated with an interstate billboard sign that is 50 feet wide by 20 feet high and is mounted on two 16-inch diameter round steel post supports. The top of the billboard is 80 feet above the ground level, and the sign is located in rural Nebraska on a flat and open site. We'll be using the wind load provisions in the 2022 edition of the ASCE 7 standard for this example. I would be remiss if I didn't mention that this example originally comes from a textbook by Narendra Talley. The Talley textbook is a good one, however, it is more than 20 years out of date at this point, having been published in 2003. In this video, I have updated the example as it appears in the Talley textbook so that it is consistent with the 2022 edition of the ASCE 7 standard. In Part A of this example, we determine the general wind load criteria, including the base wind velocity v, the elevation factor k sub e, the topographic factor k sub zt, and the velocity pressure coefficient at the top of the billboard, k sub h. Finally, we calculated the design velocity pressure at the top of the billboard, q sub h, as 35.46 pounds per square foot. If you missed the video for Part A of the example, you can watch it using the link shown here. In Part B of the example, we determined the force coefficients and wind forces associated with the three wind cases that are required to be considered for the billboard. For wind case A, the case of a direct and uniform wind acting on the sign, we found that the critical post carried 29.69 kips and that the bending moment at the base of the post was 2,078 kip feet. For wind case B, the case of an eccentric torsional wind acting on the sign, we found that the critical post carried 49.48 kips and that the bending moment at the base of the post was 3,464 kip feet. And then finally, for wind case C, the case of an oblique wind acting on the sign, we found that the critical post carried 37.77 kips and that the bending moment at the base of the post was 2,644 kip feet. If you missed the video for Part B of the example, you can watch it using the link here. In all of these calculations, however, we accounted only for the wind acting on the 50-foot by 20-foot sign, and we neglected the effects of the wind acting directly on the round posts themselves. The goal of this part of the example, Part C, is to calculate the load resulting from the wind acting on the posts themselves. Later, in Part D, we will investigate the effects that an alternate topography might have on the wind loads acting on the billboard. To determine the wind forces on the posts, we'll turn to Section 29.4 of ASCE 7, which addresses wind loads on chimneys, tanks, and similar structures, and we'll use equation 29.4-1, which is shown here. In this equation, Q sub z is a velocity pressure at an elevation z measured relative to ground level. K sub d is a directionality factor. G is a gust factor. C sub f is a force coefficient. And A sub f is the area of the structure projected on a plane that is perpendicular to the direction of the wind. We'll address the velocity pressure Q in a few minutes. The directionality factor, K sub d, is determined by referring to Table 26.6-1 of ASCE 7. In that table, there is a group of entries associated with chimneys, tanks, and similar structures. Since our posts are round, we will take the directionality factor as 1.0. Recall that the directionality factor for the sign itself was taken as 0.85. However, since the posts are round, the effect that the wind has on the posts is theoretically the same regardless of which direction the wind blows. So in this case, we'll take the directionality factor as 1.0 instead. Next is the gust factor G, and we'll take this value as a given value of 1.0945. The calculation of the gust factor is complex and beyond the scope of this example. You can refer to Part 2 of this example for some more background on this. To determine the force coefficient, we'll refer to figures 29.4-1 through 29.4-4 of ASCE 7. As you can see here, each of those four figures addresses a similar but slightly different type of structure. Figure 29.4-1, shown in the upper left, addresses chimneys, tanks, and similar structures. Figure 29.4-2, shown in the lower left, addresses open signs and single-plane open frames. Figure 29.4-3, shown in the upper right, addresses open structures such as truss towers. And Figure 29.4-4 addresses circular bins, silos, and tanks. Since a chimney is tall and slender, like the posts supporting the billboard in this example, I will select Figure 29.4-1 as being most appropriate for our current case. Looking more closely at Figure 29.4-1, we can see that the force coefficient C sub F depends on the ratio of the height of the structure to its diameter, or h over d, as well as the type of the cross-section and the surface condition of the structure. Note that there is a comparison of d times the square root of q sub z to the constant 2.5 in the cross-section definition. Another thing that is important to note is that the velocity pressure q sub z in this case is evaluated at different elevations z over the height of the structure. This is different than what we did in part 2 of the example when we calculated the wind forces acting on the sign itself. In that case, we used the velocity pressure at the top of the billboard, q sub h, to calculate the wind loads. In that case, we used a single value of q despite the fact that the sign has an elevation that ranges from 60 feet to 80 feet above the ground level. We did this because the equation that we used to calculate the wind loads on the sign, equation 29.3-1, explicitly references q sub h, which is a velocity pressure at the top of the sign. However, when we're looking at the posts, we use equation 29.4-1 and figure 29.4-1, which both instruct us to use q sub z instead of q sub h, and q sub z actually varies over the height of the posts. Recall that the velocity pressure is calculated as 0.00256 times k sub z times k sub zt times k sub e times v squared. In part 1 of this example, we determined that v is equal to 107 miles per hour and that both k sub e and k sub zt are equal to 1.0. The velocity pressure coefficient k sub z is a function of z, the height above the ground level, and the exposure condition for the site, which was determined to be at condition C. Looking at table 26.10-1 and focusing on the column of values for exposure condition C, we can see that the value of k sub z at elevation z equals 80 feet is equal to 1.21. Since this elevation corresponds to the top of the sign, this is also k sub h, the value that was used in part 1 of the example. To calculate q sub z for the posts, we need to look at elevations ranging from 0 feet to 60 feet. Note that the value of k sub z is constant from 0 to 15 feet, and then the values of k sub z are tabulated at 5-foot elevation increments at first, then at 10-foot increments, then at 20-foot increments, and so forth. For the purposes of this example, I will evaluate the velocity pressure from 0 to 15 feet, from 15 feet to 30 feet using the value of k sub z that is tabulated for z equals 30 feet, and then from 30 feet to 60 feet using the value of k sub z that is tabulated for z equals 60 feet. If we so desired, we could calculate k sub z, and thus q sub z, at more elevations, or even continuously, from 15 feet through 60 feet. But for the purposes of this example, 3 regions will suffice. I'll start the process of calculating q sub z by evaluating all of the variables except for k sub z. With that, we are left with q sub z equal to 29.31 pounds per square foot times k sub z. Next, I'll calculate q sub z at each of the 3 elevations that we identified on the previous slide. That is, at z equals 15 feet, z equals 30 feet, and z equals 60 feet. When I calculate these, my preference is to arrange them with the lower values of z at the bottom and the larger values of z at the top, so that the values of q increase vertically, much like the actual pressures on the structure. Finally, if we so desired, we could calculate the velocity pressure at a value of z equals 80 feet, And since this elevation is at the top of the structure, where z is equal to h, this value of q sub z is, by definition, q sub h. Recall that the velocity pressure represents the dynamic pressure exerted by the wind before it hits a specific surface, and it can be thought of as the raw power of the wind at a specific height z above the ground. However, since the velocity pressure is the dynamic pressure exerted by the wind before it hits a specific surface, sketching it as I have on this slide as if it were a pressure acting against the structure is technically incorrect. It's convenient, however, to sketch it in this way to illustrate how the velocity pressure increases over the height of the structure. One visual cue that I use to distinguish the velocity pressure from an actual design pressure is that I have sketched the velocity pressure in blue. Later, after we multiply by the force or pressure coefficients, I will sketch the actual design pressures in red. In any case, the velocity pressure acting on the sign itself isn't needed for this part of the example. I have calculated and shown it here only to illustrate that the velocity pressure increases as a function of z, the height above the ground level. In other words, the higher above the ground, the higher the velocity pressure is. Returning to figure 29.4-1 and zooming in a bit, we can see that we still need to know the value of d times the square root of q sub z, and we also need to know the ratio of the height of the post to their diameter, or h over d. We can evaluate the value of d times the square root of q sub z at any height above the ground. So at z equals 0 feet, d times the square root of q sub z is equal to 6.655, and at z equals 60 feet, d times the square root of q sub z is equal to 7.654. These values are compared to the constant of 2.5, and we can see that we are well above 2.5 over the entire height of the posts. Next, we can evaluate h over d, and taking the height h as 60 feet and the diameter d as 16 inches or 1.33 feet, we find that h over d is equal to 45. With that, we can return to figure 29.4-1, and using the column for h over d equals 25, along with the row corresponding to a moderately smooth, round cross-section, we can see that the force coefficient C sub f should be taken as 0.7. With the force coefficient determined to be 0.7, we can now turn our attention to the last variable, which is the projected area of the post, A sub f. In this case, the projected area of one post is equal to the exposed height of the post multiplied by its diameter. With the assumption that the wind is blowing directly at the face of the sign, the projected area on the left post would be the area highlighted in red here. So A sub f is equal to 60 feet times 16 inches, which is equal to 80 square feet. Now, that being said, since I have elected to break the velocity pressure into 3 zones over the height of the post, I won't actually use this value of 80 square feet, however. As you will see in a moment, I will use a slightly different approach instead. Instead of multiplying by the projected area of the post, A sub f, I am going to multiply by the projected width of the post, W sub f. What this means is that I will end up with a uniformly distributed load in units of pounds per linear foot. Over the height of the post, ranging from the ground level to 15 feet, we can calculate the force on the post as 24.91 pounds per square foot times 1.0 times 1.0945 times a force coefficient of 0.7 times the width of the post, 1.33 feet, which is equal to 25.45 pounds per linear foot. Similarly, over the height of the post ranging from 15 feet to 30 feet, the force on the post is 29.34 pounds per linear foot, and over the range from 30 feet to 60 feet, the force on the post is 33.83 pounds per linear foot. Next, we can calculate the force resultants for these 3 height ranges. We can find that the total force acting over the first 15-foot segment is equal to 381.7 pounds. The total force acting over the second 15-foot segment is equal to 440.1 pounds, and the total force acting over the 30-foot segment is equal to 1,015 pounds. Finally, we can calculate the moments that each of these force resultants create about the base of the post. Each of the force resultants acts through the center of the loading that it represents. Thus, we can locate the lines of action of each of the resultants like this. Then we can actually calculate the moments. The moment that the first force, the force closest to the ground, creates about the base of the post is equal to 381.7 pounds times 7.5 feet, or 2.86 kip feet. Similarly, the moments that the second and the third force resultants create about the base of the post are 9.91 kip feet and 45.67 kip feet, respectively. The sum of these three moments is equal to 58.44 kip feet. Recall from part 2 of this example that wind case B governed and resulted in a load in the critical post of 49.48 kips and a moment at the base of the post that is equal to 3,464 kip feet. If we consider both the effects of the wind acting on the sign and the effects of the wind acting on the post, we end up with a total force in the critical post of 51.32 kips and a total moment at the base of the critical post of 3,522 kip feet. So in this case, the effects of the wind acting on the post amount to less than 2% of the total wind effects. Still, this example is useful to illustrate the process that is used for calculating the wind loads on the posts, which is slightly different than that is used for the wind that is acting on the sign itself. That brings us to the end of part C of this example. In summary, when we calculate the wind loads acting on the sign itself, we use a velocity pressure Q sub h at the top of the structure. However, when we calculate the wind loads acting on the posts, we use a velocity pressure Q sub z at the various elevations over the height of the posts. Other differences that we encounter in calculating wind loads on the posts as opposed to the sign itself include different directionality factors and different force coefficients that are associated with the characteristics of the structural components. Finally, as time permits, I will post an additional video showing an alternative approach to calculating the wind loads on the posts using refined load regions. And finally, in part D of the example, we will consider the effects that alternate topographies might have on the wind loads acting on the structure.